equal to plus minus of k minus 1. We have taken the square root in this equation. So 2h equal to plus minus k minus 1, and we have to find the locus of point P. So we replace h by x and k by y. So the final locus of point P becomes 2x equal to plus minus y minus 1. This is the required locus of the point P. Hi students, and welcome to this lecture, which is known as differential equations. Now this lecture does not only form an integral part of calculus or mathematics, but we will also see that differential equations are widely applied to model natural phenomena, engineering systems, and many other situations. For example, in chemistry it is applied to the study of radioactive decay. In physics it's applied to Newton's laws of cooling. In mathematics you will see that they are applied in the study of orthogonal trajectories of curves. They are applied in population dynamics, quantum theory, heat transfer, in astrophysics, geophysics, and so many diverse fields. So that makes it very much important for us to study this chapter in depth. So let's begin. So once again, the very standard doubt: what are differential equations? We can say that it is an equation involving independent variable, dependent variable, and the derivative of dependent variable with respect to independent variable. So it is an equation and it involves the independent variable, the dependent variable, and the derivative of dependent variable with respect to the independent variable. In simple words, we can say that it is an equation that relates x, y, and different orders of derivative of y with respect to x. So this is an equation in which you will find x, you will find y, and you will find derivatives of y with respect to x. This could be dy by dx, or d square y by dx square, or d cube y by dx cube, and so on. For example, if I say x times dy by dx plus 2 times y equal to 0, here we see that this is an equation in which we find x, we find y, and we also find the derivative of y with respect to x. Similarly, if we consider this equation d square y by dx square equal to x plus y, again you have x, you have y, and you have the second derivative of y with respect to x. So these all are examples of differential equations. The next is order of differential equation. Now order of differential equation is the highest order derivative of the dependent variable with respect to the independent variable. So we can say that the order of the highest order derivative of dependent variable is y with respect to x. So if I say that d square y by dx square plus y equal to 0, now this is second order, because the highest order derivative here is this one, and this is a second order, and so we can say that this entire equation has an order of 2. Similarly, if we consider this equation d cube y by dx cube minus d square y by dx square plus y equal to x, here we see that this is a third order, because the highest order derivative here is d cube y by dx cube. We also have a second order derivative, but since we have a third order derivative, we take this into account because this is the highest order derivative, and so the order of this entire differential equation becomes 3. The next concept is degree of a differential equation. Now the highest power of the highest order differential coefficient appearing in the polynomial form of the differential equation is called as the degree of differential equation. So it is actually the highest power of the highest order differential coefficient. So what we can say is the degree of differential equation is nothing but the highest power of the highest order differential coefficient. So for example, if we consider this equation y plus dy by dx whole square plus x square equal to dy by dx. Now we see that this is a first order differential equation, because the highest order differential is 1, dy by dx, and actually we see that this is having a power of 2, so the degree would be 2. Thus we can say that the degree of differential equation is the highest power of the highest order differential. There is a term dy by dx here also, but we consider the highest power of highest order differential to be the degree of differential equation. Thus here 2 is the degree of differential equation. Now forming differential equations. Now how are we going to form differential equations? Here what we do is We differentiate the equation of curve till the unknown constants are eliminated. To form a differential equation, first of all we must have an equation of curve and it must be having some unknowns. So what we do is we differentiate this equation as many times so as to remove those unknown constants. For example, if we consider this equation y equal to ax, now this equation y equal to ax represents a family of straight lines. Here we see that a is an unknown constant. So what we do is we differentiate both sides with respect to x. So dy by dx would be equal to a. Now we know the value of a, which is dy by dx. We substitute this value over here to get y equal to x times dy by dx, and hence this is a differential equation. So the differential equation of family of straight lines given by the equation y equal to ax is y equal to x times dy by dx. Let's consider one more example. Find the differential equation whose solution represents the family of curves y equal to a times sine of x plus b. Now we have y equal to a times sine of x plus b, and we have to find the differential equation whose solution represents this family of curves. So we write y equal to a times sine of x plus b. Let us say that this is number 1. Here we see that a and b are two unknown constants, so we need to eliminate these two unknowns. What we do is we differentiate both sides with respect to x. Thus dy by dx would be equal to a times cos of x plus b, as a differential coefficient of sine of x plus b is cos of x plus b. So dy by dx equal to a times cos of x plus b. Again we differentiate with respect to x. So d square y by dx square would be equal to minus a into sine of x plus b. Let us name this as equation number 2. Now we see that a times sine of x plus b is equal to y, and minus of a times sine of x plus b equal to d square y by dx square. So from 1 and 2 we can write as d square y by dx square is equal to minus y, or d square y by dx square plus y equal to 0. This is the differential equation whose solution represents the family of curves y equal to a times sine of x plus b. Thus this is a second order differential equation where the degree is 1. Now we are going to see how to solve differential equations. The entire chapter is actually based on solving differential equations. So one by one we are going to see different methods of solving differential equations. The first method is separable variables. So if the differential equation is of the form of dy by dx equal to f of x comma y. So if we have got the differential equation of this form, which can be reduced to the form of dy by dx equal to g of x into h of y, then we write dy by h of y equal to g of x into d of x, and this way we have a function of y with dy and we have a function of x with dx, and this can be easily solved. So in the method separable variables, what we have is we have dy by dx equal to some function of x into some function of y. So this can be separated and the function with y can be brought to the side of dy and the function with x can be brought to the side of dx. So we have separated this function into two parts, one part comprising of y with dy and the other part comprising of x with dx. Let's try to solve an example that will throw more light on this. This problem appeared in IIT JEE 2007, and it says that the differential equation dy by dx equal to under root of 1 minus y square divided by y determines a family of circles with option number A is variable radii with a fixed center at 0, 1, variable radii and a fixed center at 0, -1. Option number C is fixed radius 1 and variable centers along the x-axis, and option number D is fixed radius 1 with variable centers along the y-axis. So in this problem we have been given a differential equation and we have to find out which of the four options is correct. So the first step is to solve this differential equation. Now dy by dx is equal to under root of 1 minus y square by y. Now we can say that dy by dx is equal to a function of y into a function of x. Here a function of x is nothing but constant. So what we do is we bring this expression which comprises only of y to this side of dy and we bring dx to this side. Thus y times dy divided by under root of 1 minus y square is equal to dx. Now we integrate both sides. So the integral of this is minus of under root of 1 minus y square. The integral of dx is x plus a constant of integration. So minus of under root of 1 minus y square is equal to x plus c. Now we square both sides to get 1 minus y square equal to x plus c whole square, or x plus c whole square plus y square equal to 1. Now this is an equation of a circle, the center of which is minus c comma 0 and the radius is equal to 1. Thus the differential equation when solved gives x plus c whole square plus y square equal to 1, which is the equation of a circle, the center minus c comma 0 and radius 1. Now this is nothing but option number C, and so we can say that option number C is correct. Let's try to solve one more example. Solve the differential equation 1 plus 4x square into dy equal to y cube into x dx. So we have to solve this differential equation. The differential equation given is under root of 1 plus 4x square into dy equal to y cube into x into dx. We bring y cube to this side of dy and we bring this term comprising of x to this side of dx. Thus dy by y cube is equal to x times dx divided by under root of 1 plus 4x square. Now the integral of this part is very easy. For this part, let's do a substitution that let u equal to 1 plus 4x square. So we write 1 plus 4x square equal to u. So du would be equal to, we differentiate this to get 8x into dx. Now we substitute the value of x over here to get dy by y cube equal to 1 by 8 into du divided by under root of u. So what we do is we integrate both sides to get minus 1 by 2y square equal to 1 by 8 into 2 into under root of u plus k. K is again a constant. We again substitute back the value of u. So minus 1 by 2y square equal to 1 by 4 into under root of 1 plus 4x square. Thus this is the final solution of the differential equation under root of 1 plus 4x square into dy equal to y cube into x dx. So this was all about separable variables. The equations reducible to separable variables. Now in this method we won't be given directly a differential equation which could be solved by separable variables. Here we have to perform some trick or some modification so that the equation reduces to a form that can be easily solved by the method of separable variables. But how we do that? Let's see. If the differential equation is of the form dy by dx equal to f of ax plus by plus c, that is dy by dx is a function of ax plus by plus c, then we cannot solve this by separating variables directly, as we cannot split it into a function of x and a function of y. But by substituting ax plus by plus c equal to t, we can reduce this into separable variable form. How? The differential of this would be a plus b times dy by dx equal to dt by dx. So we substitute the value of dy by dx in this expression in the form of dt by dx, and thus the differential equation would be in the form of variables x and t, and which can be easily solved by the method of separable variables. Let's try to see an example. Solve the differential equation dy by dx equal to cos of x plus y. So we have to solve the differential equation dy by dx equal to cos of x plus y. Can we solve this equation dy by dx equal to cos of x plus y by variable separable method? Yes, we can do that, but there is some modification involved. Let us substitute x plus y equal to t. So this is a function of x and y, and thus we substitute x plus y equal to t. Now differentiating both sides, we get 1 plus dy by dx equal to dt by dx. So this equation reduces to dt by dx minus 1 is equal to cos of t. Now we can say that this can be easily solved by a variable separable method. So we bring 1 plus cos t to this side of dt, and we bring dx to this side to get dt by 1 plus cos t equal to dx. Now this can be easily solved. What we do